So yeah, our project is privacy-aware neural networks, so classification and training. And I'm Nitin, he's Ali. And then we have three amazing supervisors, two of whom are here, Matt, Adria, and Varun. And so we're gonna just start and try and motivate the problem first. And then eventually we're gonna discuss about how we're trying to mitigate these challenges. So, data-driven models in the recent times, in particular deep learning models, have been really successful in predicting stuff, beyond the realms of the earlier models that they could. But then there are a couple of challenges with these kind of things because they're really compute intensive. So what people usually do, they outsource their computation to the cloud, like Amazon, Azure, and these kind of services. And this might not be ideal in many conditions, which we are going to discuss. And then there's also as you increase the amount of data, these models scale fairly well in accuracy. So it's always a good idea if we can collaborate data across multiple units. So there are conditions like Google and Facebook, they're competitors, but they would want to learn something on their data together, or they would want to use their users' data, wherein privacy is really a key thing, but at the same time, they would really want to be able to use this. And so the challenge with these kind of things is the privacy. So if you want to work with health data or for example, financial data, it might not always be ideal to use cloud or collaborative data under normal conditions. So people propose encryption or basically encryption or MPC-based protocol for performing these kind of computations over a neural net or a data-driven framework. There are three major techniques that we've been proposed to be able to mitigate these privacy concerns. So one is homomorphic encryption, other is multi-party computation, and then there's differential privacy. So we're going to basically restrict ourselves to these two basic techniques that we're working on, homomorphic encryption and MPC. So in a homomorphic encryption settings, what happens is, so basically these are like two of our supervisors, that's Adria and that's Matt. And so suppose Adria wants to outsource his computation on some text M to Matt. So what he can do is he can encrypt his entire input array and send it to Matt. He can perform some kind of operation on that encrypted text and send it back to Adria. So in the entire process, at no point Matt gets access to the clear text M. But at the same time, he's able to compute these operations. So we're going to discuss the challenges with these techniques that might not always work. But the idea is there's always an analogous operation in the encrypted domain, which we can perform on the encrypted text and get back the plain text. Similarly, there's multi-party computation protocols. So we might club it with encryption in some ways, but in general, what it means is we kind of distribute our data across multiple non-colluding parties. So the underlying assumption is those parties never come together and try to collude. But so suppose the message still is M, and then there's a third party who wants to compute this f of M on some message M. So he'll distribute the inputs between Adria and Matt, and then they can compute it together in some ways, and the final computed function is shared across them as well. So none of them actually get access to the original data, and they do not get access to the final computation as well. And this some ways works, in some ways works. And why are we actually doing this? Because in data-driven settings, or for example, in neural networks, you would usually want to do linear operations, which is matrix vector multiplication, and then followed by a nonlinear operation. So it's all about computing functions, and we want to be able to compute it on encrypted data. So as promised before, these techniques do not fairly scale well, and there are like all kind of challenges with these techniques. One of the major challenges, they are compute intensive, in particular like homomorphic encryption. If you want to be able to do a certain finite number of operations, still fine, but if you want to be able to do fairly large number of operations, as you would expect with a neural network, it does not scale quite well. It takes a lot of time to compute that, and then there's communication-based limitations, especially in multi-party protocols. So you end up transmitting your shares across multiple parties, and then there's a lot of offline phase of computation as well. So this results in unbearable amount of communication in a lot of settings. And then we are limited by number of operations. So ideally, these techniques are basically suited for linear operation or polynomial operations. I mean, of course, we can approximate operations polynomially always, but then that would result in high degree operations, which would not always be ideal. And most of these techniques also work well in fixed point operations. So most neural networks, they would have used like float 32 or 32-bit floating points. So that makes it a little difficult to use these techniques just out of the box. And then there's variability across protocols and standards. So there's MPC, there's homomorphic encryption, which has computational privacy bounds. MPC have different kind of privacy bounds, and within them they have multiple protocols, which makes it fairly difficult to decide upon which protocol we would want to use based on execution time and privacy guarantees that they have. And for tackling these kind of problems, we have worked on two different domains. One is from the machine learning point of view, wherein we are trying to condense the machine learning models and make them more crypto-friendly. And another thing that we are working on, making these protocol MPC and encryption more machine learning friendly. So now Ali is going to discuss the machine learning point of view.
Okay. Until now, we see that why privacy is important, and we talk about the privacy enhancing technology in MPC and homomorphic encryption. But now let's analyze the neural network that we want to use for classification and training from cryptography perspective and see the bottleneck. Let's consider a supervised deep neural network. In the supervised deep neural network, we have classification and training. In the classification, we start by the input, we pass it through the layers, and we predict the output for this input based on our model. But in the training, we have the backpropagation of the error plus to this forward pass. So in the training, we start by the input and pass it again through the layers. And as we have the desired output in the training, we can define the loss function based on the output of the model and the desired output, and based on the error, which is the derivative of loss, we can backpropagate the error from the end to a starting point, and then based on the error, we can see the responsibility of each layer and each neuron on the error that is produced in the output, and change the weights and parameters of the model based on the error of each layer. So as you see, in the classification part, we should do some matrix multiplication followed by nonlinear activation function. But in the training, apart from that, we need to do some derivative and backpropagate the error. So as we have many multiplication and nonlinear activation function in the deep neural network, they are slow in homomorphic encryption and multi-party computation. So what we can do, we are looking at both of them, classification and training, to see what we can do to improve the computation time and train the model in a private way. For the classification, we want to optimize the neural network through the regularizing the architecture. So we use the DropNeuron to simplify the architecture of the neuron. For example, during the training, you start by this architecture, and at the end, you come up by the simplified version of this that is give you reasonable accuracy, but it reduces the computation time as well. So let's consider this case that we have a 3 neural network layer, input layer, hidden layer, and output layer. W1 and W2 are the parameters that connect the input layer to hidden layer and hidden layer to output layer. And this model output the Y with this equation. So for example, we want to drop this neuron, the first neuron of the hidden layer. We need to penalize all of the incoming weight of this neuron, which is the first column of the W1. If we can penalize this, the first column of the parameter, so we can penalize the incoming weight of that neuron, and we should be able to penalize the outcoming weight of this neuron as well, which is the first row of the W2 matrix. And during the training, we add this to regularizer to the loss function that I discussed in the previous slide, and we train the model, and at the end, we come up by a simplified version of the neural network that can help us in reducing the computation time during the classification, but not training, because in the training we need to do all of the multiplication, and it doesn't change because at the end of the training we drop the neurons. So we evaluate the drop neuron in the MNIST dataset, which is the digit grayscale images. We use the binary neural network because it's in the favor of the MPC and homomorphic encryption, and we implement it in TensorFlow. And the structure that we use for MNIST in binary neural network is the common structure of binary neural network that is proposed by original paper of binary neural network with Benjio's team. So there is 3 hidden layer. They are the size of them are the same, 2048, and the input is 784. So as you see in each layer, we are able to reduce the number of the neurons, even in the input layer, because there are many redundancy in the digit images of MNIST. So for example, in the second hidden layer, we are dropping more than 1,000 of 2,000 neurons, which can help us in decreasing the number of inner products that we need in the classification part that I discussed, because we are reducing the number of the neuron, and we are reducing the size of each layer, which come up by reducing the size of parameter that we want to multiply in the matrix multiplication. So we can achieve the reasonable accuracy by acceptable computation time by using this trick in the classification part. We are looking at the training as well. So for training a model in a private way, there are a few papers that most of them, they just use a shallow neural network and a simple handcrafted model, and they still works on the fixed point, but the size of the bit that they use, it's large, so it's with high precision. But there is one exciting paper that use integer during the training, not only for weight and activation function, but also for the gradient of the loss function based on the activation function and weight as well, by quantizing each of weight, activation function, error, and gradient during the training. And they just represent weight, for example, with 2 bits and activation with 8 bits. As you see, for example, in the forward pass that we saw it before, they quantize the weight, and then when they multiply it by activation function and compute the nonlinear activation function of the next layer, and at the end, again, the output of this will be quantized, and the same for back-forward propagation. And now what we are doing is designing a new MPC protocol based on this integer training to be able to train the model in a private way with MPC. And now Nitin is going to introduce the ship that we are guiding.
So as I talked about encryption earlier, the thing with these protocols is that there's limitations with the different kind of protocols standard that they have, and it's not always possible to compare. But so we were involved in this sheep project. So what we're trying to achieve out of this to be able to standardize these kind of protocols, not really standardize, but benchmark these protocols in some ways. So there's this HClib library. This is a IBM IBM library, which is based on BGV encryption. This is a fully homomorphic encryption library. Then there's Seal, which is a Microsoft product, and this is based on FV encryption scheme. Then there's TFHE, which is a fully homomorphic encryption library again, and which supports bootstrapping on 1-bit numbers. And then there's the standard libfailure library, which is standard additively homomorphic library. And so, I mean, the idea behind this platform is to be able to combine all such libraries and then use a common abstract framework to be able to compute operations across these libraries and benchmark them. So this is one of the things that we have been working on as a part of our internship, but this project basically is a brainchild of Agrawal and team who are working on standardizing these techniques. And another thing that we were involved in from the point of view of encryption and for using them for neural networks. So in general, we have a lot of matrix vector multiplication involved in the deep neural networks. So in general, we have situations like when we want to conduct inference on a neural network, you would have a condition wherein you have a set of weights which are freely available with the network provider, but then there's a vector which is encrypted and which is the user query, and they would want to conduct particular inference on this vector, and you would have a lot of matrix multiplication operations. So in general, when we have a plain text, you use GPUs to be able to conduct these operations in fast manner. But in encrypted domain, we have something called packing, which lets you encode a number of vectors into a number of different elements, or vectors for that matter, into a single polynomial. And then you can use this particular polynomial to compute operations parallelly. And this does work pretty well, but it does not scale well, because if you even if you want to compute a reasonably sized 512 cross 512 matrix, it takes 46 seconds in a standard framework using SEAL library. So we tried to implement a recent connotation for this, which was introduced by Halevi et al. What they try to do is they try to diagonalize the matrix and then conduct such operations, and we implemented this in SEAL, and this is about like 300 times faster than the standard naive wave multiplication that they have in SEAL. And this would be like really scale well for a reasonably sized neural network. So that's another thing that we're working on. And that's pretty much it. And that's the final advertised picture by Ben.
Thank you.